All right, hey everybody. Looks like everybody is here. So everybody is muted, but if you go to the box in the upper right-hand corner, there is a question tab, and right next to the X is what it looks like, kind of a push pin. You can click on that push pin and that question box will pop out so it's bigger, and you can enter your questions into there. So as I'm going along, just go ahead and enter the questions. I'll keep my panel open so I can see the questions and I will answer them as we go. So today we're going to talk about ACTINA pellet softening for water production. Topics go through why and when to consider pellet softening. Get into some details about the process itself. Show you a few installation examples, talk about our piloting, our pilot tests to date, and give you some information on what our pilot unit looks like. And then, if there's broader questions and answers, we can go through that at the end. So why use pellet softening? So it's a very simple treatment process. You can operate it with caustic or lime. There's no moving parts within the process reactor. It is a fluidized bed. So in relationship to a conventional lime softening, it does produce more stable operations as far as effluent hardness levels. Not only do you reduce hardness, but you reduce iron, manganese, fluoride, organics, in addition to the hardness, and that all just kind of happens with no additional effort. You can increase your organics removal, but the iron and manganese just kind of happen at the same time as the hardness reduction. There's a very small process footprint from a length to width standpoint. It can be tall, but it's a very small length and width footprint. Proven technology around the world. If you're comparing it to some other options like a membrane, you don't have the brine disposal to worry about. And if you're looking at conventional lime softening, obviously you have that lime sludge, that watery lime sludge that you have to dispose of. So the pellets we produce with pellet softening are a good alternative to those two. So the pellets we produce are self-dewatering and easily get to 95% solids, and you can reuse them for so Tanya had asked a question, are there any landfills in Florida that have agreed to take the pellets? So the pellets themselves, they're not toxic. It's really calcium carbonate. So I would say I haven't asked any landfills specifically in Florida, but I know in other locations, it is not an issue to dispose of these in just a typical municipal landfill. So the other part of why you would use it is the operation and maintenance cost savings that are available with it. And we'll get into those a little bit more towards the end, but any equipment or labor associated with mechanical dewatering obviously goes away because our pellets are self-dewatering. And if you have lime sludge and you have a drying bed and some other means of handling your lime sludge, those as well can go away with the pellets, again, because they're easier to handle and are self-dewatering. If you're just simply going to take your pellets to a landfill versus when you're looking at pellets versus lime sludge, again, we easily get to 95% solids, where if you did some drying and mechanical dewatering of conventional lime sludge, maybe you get to 30 or 40% solids. So just by the simple fact that our pellets can get to 95% solids, there's pretty decent cost savings there just in the number of trips you have to make to the landfill, given the higher solids content. And of course, if you're doing deep well injection because of membrane brine, that goes away. And if you're going to operate with caustic, and you currently have a conventional lime softening plant and they have the lime silos and the Schlakers and all that, you can get rid of all the kind of labor and maintenance associated with those. And also, again, comparing it to a lime softening plant, if you run ACTINA pellet softening with caustic, you're generally going to produce anywhere from 1 to 3 NTU in the softened water. So you can significantly reduce the load, the TSS load onto your filters with pellet softening and caustic. Okay, I go through these real quick. So when to use it, if you have current or future disposal limitations on your lime sludge or your brine, that's really been the main driver. Either it's the lime sludge or the disposal of the brine. That's in most of the projects that we're currently working on in the US with pellet softening. Those two are one of the two drivers. If you need to expand your capacity, but you don't have the space to do it with, say, a conventional lime softening, you can also use it as pre-treatment to an existing ion exchange system to lighten the load on that ion exchange, reduce your salt consumption, and you can actually improve your media life and improve your water quality consistency by pre-treating with pellet softening. You can also use pellet softening to treat, like if you have reverse osmosis brine that if you're using RO to treat your groundwater now and you have a brine, you can actually treat that brine with pellet softening. And really anywhere you're doing water, producing water for either public or even industrial uses, pellet softening is a good option. Okay, so technology itself, basically it's a simple fluidized bed reactor that uses a catalyst, whether that's sand or crushed calcium carbonate pellets. And we basically promote calcium carbonate precipitation on that catalyst. So here's a typical ACTINA reactor where you have the flow that comes in the bottom. It goes through some flow strainers, then up through the fluidized bed portion, and it goes into this flared portion where the water slows so that the catalyst remains in the fluidized bed portion, and then your effluent comes out the top. So this fluidized bed portion of the reactor, again, is full of catalysts, whether it's sand or calcium carbonate pellets. They'll be all the size of the pellets or the sand will be different over the length of that fluidized bed based on how long it's been running and so on and so forth, which I'll get into here in a minute. But that's really where it all takes place. You'll adjust the pH at the bottom. The change in pH creates the calcium carbonate to precipitate and grow onto the catalyst that's in that fluidized bed. So reduce calcium and some magnesium hardness, and again, we'll produce these easily dewatered reusable pellets, which, depending on your raw water quality, can look something like that. So how is the influent flow distributed through the reactors? So at the bottom of the reactor is a strainer plate, and it has numerous flow distribution strainers installed. So if you take this bottom of the reactor, this portion of the reactor, and pull it off to the side, the strainer plate is what you see on top. And then the nozzles are these individual components that are actually attached to the strainer plate. So that strainer plate that you see there, and I don't know the number of them in this picture, say there's 200 strainers. So it's a metal plate, and there's holes in that metal plate. So each of these individual strainers go into those 200 holes. So this is what one of our flow strainers looks like. So what we use is a strainer that's been specifically designed over the years for pellet softening. There's a lot of advantages to it. It does a really good job of equally distributing the flow, but it also allows for material to pass through the strainer, which I'll show you here in a second when I show you more detail of what it looks like. But pellet softening is pretty straightforward, but that even distribution of the flow coming up through the reactor is really critical. So again, this strainer is in two pieces. We have a cap, and then we have this other portion. So hopefully you can see my cursor, but there's a lip right here. So this lip would sit on the strainer plate. So this would go through the hole. This side is threaded. So this lip sits on the top of the strainer plate. We just have a nut that attaches each individual strainer to the plate. So the flow comes up through the middle, comes out through these three holes. And again, this cap sits on top, and there's slits on the cap as well. So again, the purpose is to equally distribute the flow while also allowing any material that may come in with the raw water, say some small particulate or whatever, to pass and not create a clogging problem at the base. So this is a picture of multiple flow strainers installed in the strainer plate at the bottom of one of our reactors. So for chemicals, we will increase the raw water pH, and as I mentioned before, with either caustic or lime. We have the fluidized bed catalyst, which again is either sand or calcium carbonate pellets. And on the effluent side of the reactor, we will reduce the pH back down to something towards neutral, 7 or 8. And basically you want to stop that precipitation reaction before the water goes downstream, whether that's to some filters or to a membrane or whatever. So you just simply adjust the pH back down. So let me focus on increasing the pH real quick. So again, you get the same reactor diagram. At the bottom is where we have this removable spider, and what we do is we inject, again, whether it's caustic or lime, we used softened carrier water to deliver that pH adjustment chemical to this spider, which again sits at the bottom of the reactor just above that strainer plate I showed you in the previous slide. So if you take that section away again, the blue plate is the strainer plate, and then you see now they're kind of gold colored flow strainers. And then right above that is that circular support structure, which we would call a spider or chandelier. And on that, you will see there's 3 nozzles. Each nozzle has a pH adjustment line going to it and a softened carrier water line going to it. So the purpose is to bring those in individually and then combine them together under pressure in the nozzles so that they disperse out through each of the nozzles. The number of nozzles in any given spider is driven by the diameter of the reactor. So the bigger the reactor diameter, the more of these nozzles you will have. But in this particular example, you have 3 separate nozzles on this spider. So again, this thing is suspended from the top. In the picture to the left, you can see there's a cable here attached to it. So this goes all the way to the bottom of the reactor and then sits there, and it is connected at the top. So if you need to remove it, it easily can be removed without having to drain the reactor itself. When I mentioned the flow distribution strainers, these nozzles are also something that we at Veolia have designed over the years to be very effective in dispersing of the chemical while also minimizing the amount of scale that goes on with these nozzles. And here's a close-up of that individual nozzle. So at the top of the reactor, in a separate panel, we'll have a rotometer and pressure gauge on each one of these lines going to the nozzle. So while this thing is sitting at the bottom of the reactor, you can have a good idea by looking at these rotometers and these pressure gauges if there's some type of issue going on, whether you have, your flow isn't the same between the three nozzles, or you see elevated pressure in one of them. Then again, the intent of having this thing suspended from the top is if you do see some type of issue, you can pull it up, pull it out of the reactor, inspect it, do what you need to do to it, and then put it back in pretty easily. So continuing, so the fluidized bed with the catalyst. So it's added either by a pump or an inductor into the side of the reactor or to the top of the reactor. And there's a couple of different ways you can do that. Depending on the size of the reactor, I would say the most common way is with some type of bulk storage, whether it's a bulk bag system, which holds like a 2,000-pound super sack, or a small or large size silo that holds the catalyst. And you would basically just convey that material into either a slurry tank, like on the picture on the left, which would have a mixer, and then you could pump directly out of that slurry tank into the reactor. Or even simpler is you can drop that catalyst into an inductor, which is the blue funnel, and basically there's some water that comes into the side of the funnel to help wash the material down, and it goes down at the bottom of that funnel, and there's some plant water that's going by under pressure, and it basically just educts the wetted catalyst into that pipe, and then that will carry it to the reactor. So as I had mentioned, you can either inject it into the side of the reactor or drop it straight into the top. Either way is fine. So the fresh catalyst is added about after every 2 or 3 pellet extractions, which I'll get into here in a second. So it's not something you're doing continuously. It's fully automated, and it's maybe once or twice a day, depending on the size of your reactor and your water hardness. But you don't have to stop flow to the reactor or anything like that. It keeps producing water. And then again, the pH adjustment, you can add, some places have CO2 being added to the water, and I've seen a lot with just sulfuric acid being dripped into the outer portion of the, where our effluent comes out of the top of our reactor. Gives a little bit of mix time, and you're really just trying to get that pH back down to, between 7 and 8 to stop that precipitation reaction from occurring once it leaves the pellet softener. Okay, so when and how are the pellets extracted? So we continually monitor the pressure inside the reactor. So the strainer plate that I had mentioned earlier that has our flow strainers is here. You can see the weld marks. The plate's obviously inside the vessel. But we monitor the pressure below and above, and the difference between those two we correlate to a pellet size in the reactor itself. So this is a relationship that we set up during commissioning. So there's two ways you can do it. You can use these pressure indicators, or you can just go by time, like it's ran for 9 hours, it's probably time to do an extraction. But either way you trigger the extraction, the pellets are extracted either by a pump or by gravity. So when the extraction actually happens, there'll be a separate pipe off to the side of the vessel, which basically has a valve. And once you open that valve, again, you have the pressure, the head pressure from the reactor that'll push out the pellets through that piping. It'll stay open for a certain amount of time. It closes, it flushes the line, and that's pretty much an extraction. You don't stop flow during the extraction. So what's going on inside that reactor is if you have it all, you're going to have different size pellets inside that fluidized bed portion of the reactor. So the larger pellets will be towards the bottom because they're larger and heavier. So we want to extract towards the bottom. So if you look at that picture to the right, you can see just below that pellet extraction pipe, you can see the weld marks for the strainer plate. So we're drawing off the pellets really pretty much right at the bottom of the reactor. Again, and the purpose of that is to get the larger ones out and to keep the smaller ones inside. Because again, it's a fluidized bed, so if the pellets get too big, it'll be harder to fluidize them. So you kind of manage the size of the pellets either based on this differential pressure or by time. And again, after you do an extraction, that line is flushed. The pellets will leave the reactor by gravity because of the head pressure in the reactor. If you have your pellet handling bins right next to the reactor, then you can just do it all by gravity. If you need to move the pellets to another location, and I'll give you a few examples here later on, you can have a centrifugal slurry pump in line to where, you know, you'll still just open the valve. The pellets will come out by gravity, but then you have this centrifugal slurry pump in line to help move it. If you had to move it to another elevation, or you had to push it to some bins on the other side of the plant or something like that. So we can do it either way. I would say it's probably 60% of the time they have pumps involved to move the pellets to another location. So again, as I mentioned before, the extraction of the pellets and the addition of the catalyst are all automated. So from an operator standpoint, they don't need to do anything. It all happens through the control system. So how are the dewatered pellets, or how are the pellets dewatered and handled? So as I'd mentioned before, they're self-draining. We don't need any mechanical dewatering. And a lot of times it's just these simple bins. So this bin is, you know, I've seen Baker Tank has these. It's basically just has a screen at the bottom of the bin, and that what happens, and there's probably 6 or 8 inches of headspace underneath the screen at the bottom. So obviously the pellets get extracted into this bin. The screen maintains the pellets in there, and then and also allows the water to drain out away from the pellets. And it's hard to see in this picture, but in the front of the bins, there's these drainage ports. This one is obviously a single bin, and you can see the pipe here that's coming out from the plant. So depending how close this bin is to the actual reactor, you could just do it by gravity, where you open that valve and the pellets make their way into this bin. This one obviously is outside, just has a simple tarp that you can pull over it to keep the rainwater off. The one down here is kind of a duty standby scenario, where this one is covered to keep the rain out, but you can see there's a PVC pipe that comes out here. So this is basically has a piece of rope on it, so you can change which bin. You just swing it over. You can change which bin you're discharging to, or you can move, within a bin to which part of the pellets are actually discharging into, which I'll show you here in a second to better explain that. Again, close up. These bins are sloped from back to forward. So this is the discharge line, and this particular installation does have pumps. So they pump it from inside the building up and over, and this is the discharge of those pumps. You can kind of see the rope that's attached to it, but they just move this to different locations within a bin, or they swing it over to the other bin when this one is full. And here you can see the water that's running off the pellets. Again, there's a screen maybe 6 or 8 inches above the bottom that retains the pellets but allows the water to drain off. For larger installations, higher hardness installations, it really comes down to your pellet production rate, but you may need something more substantial for the pellets. I would say all the projects we have done and worked on so far have not required this large pellet storage like this, but there is a few different versions that we have designed. But it's really just comes down to how much flow you're treating and how much hardness you're removing. In this particular installation here, they're surrounded by farmland, and the farmers come, I think, once a month and actually take the pellets and use them, I think, mostly for fill. But this particular installation doesn't have any pellet disposal at all. The farmers come and take it for free. The runoff or the drainage that you see here can be recovered and sent back to the head of the plant. It doesn't have to go to waste. So there's a lot of different options you can do with that. So this is a video that will show you're going to be looking down from the top of the reactor down onto the top of the fluidized bed. So this portion you're looking down into is the flared portion that I've shown you in those diagrams. This cable here is what is attached to the spider, which is at the bottom of the reactor. So here you look down on top of the fluidized bed, so you can see it's really nicely, evenly distributed throughout the cross section of the reactor. You can see the tubing that's going down to the spider to each of the nozzles. And this is the overflow weir. So this is just a straight edge weir that goes all the way around the top. So the softened water comes out. And if you were to adjust the pH, you could easily drop it into this outer rim. There'll be a common discharge point on one side of the top of the reactor. So you could add the acid towards that side, and it doesn't really take a whole lot of mixing, and you can achieve that decrease in pH pretty easily before it goes downstream. Let me show you just one more time. So again, what you're looking down on is the fluidized bed. This cable attaches to the spider. These hoses go down to the nozzles on each spider, or on the spider. Okay, the next one I want to show you is the actual removal of the spider itself. So this whole process took about 5 minutes, but this is the tail end of the removal. This panel behind here is what I had mentioned before, which houses the rotometers and the pressure gauges for each of the lines going to each nozzle. So you can monitor what's going on at the bottom of the reactor in that spider. So here you don't have to have flow going through the reactor, but when you lower the spider back down into the reactor, you do have to have the media expanded. But again, if there was something you wanted to look at, or you thought maybe there was a problem, you could easily pull this up, do what you needed to do, and then drop it back down. Ideally, you want to have the ability to raise this above the upper level of the reactor and be able to swing it over. And then, you have grading or checker plate or something over here where you could lower this spider back down and do what you need to do, and then, pick it back up, swing it over, and drop it into the reactor again. So this is the pellet extraction. So this was that 2-bin example that I was showing you, and you can see the discharge pipe there, and then just the rope that's attached to it where they can move it to where it's discharging in different spots within a bin or swing it between the 2 bins. But what you'll see off to the left, you'll see how quickly the water runs off these pellets. So these pellets are coming straight out of the reactor. Again, this has a pump, so it's being pumped from the pellet discharge point in the reactor into these bins. And you can start to see on the left, a little bit of water running off. Then the longer the extraction interval goes, you can see the more water starts to run off these pellets. So not only are you getting kind of direct runoff just from the top, but the water is also seeping down through the pellets and going kind of from top to bottom as well. So and again, these bins slope from back to the front, so the water simply runs off. And again, you can capture this water and send it back to the head of the plant, or you can send it to a drain, whatever you is best. Okay, examples. So we have 50 plus installations worldwide. Veolia as a company has been doing pellet softening for over 25 years. We have some large installations, we have some small ones, and we've got a lot in between. So I think we have a really good mixture of these different sizes. I would say most of what we've been working on in the US has been in that 2 to 10 MGD range. So we have a good amount of installations in those flow ranges. And so a lot of the installations in Europe and especially France, Veolia also operates some of these installations. So not only do we have a lot of good design and commissioning experience, but we also can get some return on experience from the Veolia operators that operate these different ACTINA facilities around the world to figure out what makes sense, what should we change, what should we improve. So just give you a couple examples. So Copenhagen, Denmark, there's this water provider that has multiple groundwater treatment plants, and they are in the process of installing pellet softening in all 7 of these plants. So it's kind of a neat circumstance currently, because some have already been commissioned, some are under construction, some are in early construction, some are still in the design phase. So it's kind of a neat place to get a real in-depth understanding of the different phases of what these projects will look like. In Denmark, the Veolia office also can access the consulting, so they'll do controls, they'll do full scale, the whole plant kind of layout and things like that. So again, it's a good, if there was a place to visit outside of the U.S., this is a good place to be, to get a lot of different aspects of construction, design, operation, all in one trip. There's a couple examples of the plants in Denmark. This one was commissioned in 2017. It's got 3 reactors. This is another one I believe is under construction, 4 reactors, and this is a brand new plant. So this is pretty cool to see it from start to finish. Most of these plants for this municipality just had basic, a pretty basic groundwater treatment plant, and adding pellet softening to each one of these is a fairly major upgrade for all of them to what they currently do. So it's also a good place, if you had operators that are maybe just operating a very simple groundwater plant now, where they just maybe pull it out of the ground, disinfect it, and then send it to distribution, where these operators have kind of gone through that progression from a relatively simple plant to now they have, pellet softening and filters and chem feed and all these different things. So again, it's kind of a neat place to go and kind of get the full advantage of these experiences from both Veolia and the people operating these plants. There's one in France. I just bring this one up because they actually have a CO2 stripper upstream of ACTINA, which is kind of what we currently have at the New Smyrna Beach project that I think some of you may have visited, our pilot. This one actually has just one single reactor because they're part of a regional treatment layout, if you will. So if they have to go offline for whatever reason, there's other groundwater treatment plants that can contribute to the system and make up this 1.2 MGD if they were down for whatever reason. So they were able to get away with just a single reactor. And this is just a picture of the ion exchange softener that we use for the carrier water to help deliver the pH chemicals to the spider. A little closer to home, South Adams County, Colorado. This one will have 3 reactors, 4.6 MGD each. They have a spot for a 4th reactor for future expansion. It's currently under construction. Hope to have it online sometime this winter, either winter of 2020 or 2021. But here you can see a rendering of the plant. So again, they started with 3 reactors. They have spots. They have a spot for a 4th reactor. These what you see here are the pellet storage bins. So again, this particular installation, we will be pumping the extraction up to these bins. These bins will store the waste pellets and also allow them to drain at the same time. And then they're obviously elevated, so there's a bay here, so a truck can pull in right underneath these bins and just dump the pellets into this truck, and then they can haul them off. Our reactors are approximately 25 feet tall, and then the upper portion is about 17 feet in diameter. So here you can see the actual assembly of those reactors on site. This was this summer. Came in 2 pieces, so they're pretty substantial in size, pieces of steel. So here's what they look like, all 3 installed. Again, they have a spot for that 4th reactor that's sometime in the future. From a timing standpoint, for construction, obviously they had to get these installed before they could button up the building. A couple more pictures. So this is the reactors and the filters rendering. And here's a picture of that. You can see the 3 pellet softeners in the foreground, and then the filters are in the background. And again, just the same picture, different angle. So as I mentioned, this should be operational later this year or early next year. Okay, going into some pilot testing. discussion. So our pilots are rated from 10 to 14 gallons a minute. They basically have two skids. There's the ACTINA pellet softener skid, and then we have a control panel and chem feed skid. Again, with the pilot, we can use either caustic or lime. We do have automatic control of the pellet extraction, just like you would see in a full scale, where we just have a pinch valve that would open based on differential pressure or time, and we would collect those pellets. One thing that we can do, and we've done this a lot in the pilots that we've done to date, is we have multiple sections of different heights that we can incorporate into the pilot. So if you look at the one on the left, that's kind of the base setup, and then we can add 2 foot, 4 foot, 6 foot, multiple 4 foot, so whatever sections in between to get different bed heights or reactor heights. And what that allows us to do is really optimize that bed height based on the influent water quality and the desired effluent water quality. So the height is a cost when you're, especially if you're putting this in a building. So our pilot allows us to just do variations in heights to, again, optimize where we need to be to achieve the effluent quality that we're trying to achieve for the testing. And that can come into play, it can help us if maybe avoid adding a pump station, or if there's existing buildings or something like that, we can really do different heights during the pilot to come out with the data that we need to provide the best fit for the project. Boynton Beach, Florida, just a quick summary. We did that earlier this year. Again, you got the two setups. You got the control panel skid, and then you have our actual pellet softening skid. So again, when we do pellet extraction in the pilot, we have this basically a 55-gallon drum with a hole in the top, and then a 5-gallon bucket that has some holes in the bottom of it with some window screen. And that valve opens when we extract. This valve here opens in the pilot. Pellets come out into this bucket. Again, there's a screen down here and there's holes in the bottom of this bucket, so the water drains off into the 55-gallon drum, and then we retain the pellets in this 5-gallon bucket. In Boynton Beach, they had decent levels of iron in the raw water, so the pellets, again, we'll remove the iron as well as the hardness, so the pellets were more of a wet sand color versus the white pellets that I had showed you early. Doesn't really change the makeup of them. It's just the color is a little bit different depending on what might be in the raw water. That stencil you see is actually in millimeters. So these were about 1 millimeter in diameter, 1.5 millimeters in diameter, the pellets we extracted. But what we did, so we ran for a month at Boynton Beach, and in our pilot testing report, we worked with the operations manager at Boynton Beach and got some of their operating costs based on their conventional lime softening plant. And we, compared to how we ran the pilot and the results we got, we're able to do some direct comparisons between the two. And when we used caustic with ACTINA, and again, this is looking at chemical costs and sludge handling costs, we were able to potentially save them up to $280,000 a year. And when we used lime with ACTINA, we were able to save them up to $125,000 a year compared to their existing operations. And again, most of that cost savings was related to chemicals and their sludge handling. There's a lot of other advantages associated with that we can talk about at a later time, but that was really the crutch of those cost savings. And for Boynton Beach, their softened water total hardness goals was, from 80 to 120 milligrams per liter, which we were easy, or we could achieve pretty easily with either caustic or lime. So I'm actually doing a webinar next week on the 12th, I believe, through TPO with Boynton Beach, an engineer from their engineering group, just to kind of go over the pilot and talk about some of the results, and then go over these cost savings that we were able to show based on the piloting results. New Smyrna Beach, we just finished up there in October. We're in the process of writing the report and doing a similar cost analysis of what we showed in the pilot versus what they're currently doing with their conventional lime softening. So hopefully end of November, we'll have that all wrapped up and have those numbers generated to see how we stacked up against their conventional lime softening. I would say the first take, it looks similar. The biggest difference, I think, is if you have how you handle the conventional lime sludge. So if it's Boynton Beach landfills it, I'm not exactly sure what New Smyrna does, but I think it's a little different than what Boynton Beach does. But anyways, we'll have those numbers late November, early December. One last pilot I wanted to talk about. This was out in Colorado. This was pretty interesting, where it's an existing RO groundwater treatment plant, and they've been discharging their brine to a surface water for decades. I think the plant is 20 years old, and I assume they've been doing it the whole time. They have nitrate in their groundwater, so obviously the RO brine is fairly concentrated with nitrate. They will no longer be able to discharge that brine to the surface water because of the nitrate concentration. So the municipality was looking at options of how do we take care of this. And the first option was to keep the RO plant and then treat the RO brine with softening and then a biological nitrate removal, so that they could actually reuse that water, put it back out into the distribution system. And they compared that to actually replacing the entire RO plant with a new pellet softening facility. And as of right now, they've kind of abandoned, the plan is to abandon the existing RO facility. Again, it was about 20 years old, and go with a new pellet softening plant to treat the entire flow. So the brine issue goes away completely. So we looked at two different well fields during this pilot. One, was pretty clean, just had hardness issues, and the second one had hardness and manganese. So you can see the difference in the pellets. So the picture on the left is the where it was just hard water, and again, it's the same scale as I showed previously. Those are millimeters. Those size of those holes are millimeters. So the second one is the groundwater that had the manganese in it. So you can get an idea of the difference in the appearance of the pellets based on what's in the raw water. So we did two different well fields, and we also piloted on their undiluted RO brine. Again, at the time when we were piloting, they weren't sure which direction they were going to go in. And actually, I thought the whole time that this was the route they were going to go. But you can see here the difference in the size of the pellets when we were treating the RO brine versus, the one all the way to the left. The groundwater on the left, I want to say, had about 300 milligrams per liter of total hardness. And then the brine that we treated was almost 3,000 at the worst case milligrams per liter total hardness. So you can see the difference in the size of the pellets. If you're treating 2,800 milligrams per liter of total hardness, you're going to extract more frequently. The pellets are going to grow faster and bigger. So you can kind of see a good comparison between the two. To what I had mentioned before, so once we get into these higher hardness concentrations, we do need to go taller with our reactor. So the picture is actually what we did at this Colorado facility. We were fortunate enough to be able to put it inside a building. They had an overhead crane, so we were able to erect it, if you will, inside a building. We had to put up this temporary scaffolding along the side so that we could access the top. We are currently, that's not going to be the case where we have the ability to do this inside. So we're currently constructing or fabricating a separate structure that we will use to set it up outside. So we'll have, you know, again, these really high hardness applications. We can do various heights with our reactor, and then we'll have this second structure that they will tie in together from a support standpoint, and then the base of the pilot is anchored, and then the base of the second structure is anchored in the concrete as well. So, all right, real quick summary. These are a little generalized, but you know, from a total hardness reduction, and it really depends on the calcium to magnesium hardness ratio in your hard water, but for total hardness reduction, you're looking anywhere from 65 to 75% with ACTINA. Again, you'll get more of the calcium hardness than you will the magnesium hardness. But we do get a decent amount of magnesium hardness, and that's really driven by what pH you operate at. So if you want to focus on getting more of that magnesium hardness, you can operate, you know, in a pH of 10 or higher. But I would say most of the Florida jobs we've done so far, given the relatively high amount of calcium hardness in the water, we could operate anywhere from 8.5 to 9 pH and easily achieve the total hardness effluent goal. That's with caustic. But from a total iron reduction, you know, anywhere from 65 to 75, manganese 85 to 90, and we actually will reduce fluoride as well, depending on which pH you operate at. So, and I mentioned organics earlier. We're going to be hopefully doing another pilot in Florida where we're going to focus on enhancing organics removal by doing like a pre-treatment step to see how much better we can get on organics removal. In general, the sodium hydroxide dose is somewhere between 80 and 130, and the lime dose is somewhere between 130 and 180. So again, this is some generalizations from some recent pilots and full-scale data and things of that nature, but just kind of give you an idea of what we can do and the chemicals required to do it. So that's all I got. Bring this one back up. Anybody have any other questions? See, Tanya, you had one, but anybody else got any questions? No? Okay. So Eric, maybe we'll touch base after this. And, you know, Tanya, if you want more information, if you have, you know, one of your customers that would be interested in piloting, or you just want to talk more detail about stuff, you know, feel free to reach out to Eric or myself, and we'll continue the conversation. Okay, thanks everybody. Have a good day.